Hello boys and girls and everybody else, welcome to another science video lesson, and for today we will going to talk about something that is very integral to our daily activities. So I think without this something that we were going to discuss this session, I think we will not be able to do our daily activities in life. Alright, so what is this something that we were going to talk about this session? So come and join me as we discover this particular topic here in our video lesson for today. So let's start. And there we go. So in this video lesson, we are still in electricity and magnetism. But before we go to our topic itself about electricity and magnetism, to be exact, so I have right here a picture, so not so clear picture of our modern world. So this is a modern world. So in your area, you can take a look at your busy city streets that you have right there. All right. So in our modern world that we have right now, so what is, or okay, you can pause this question to answer, or you can pause this video rather to answer this particular question. So what do you think is the integral part of our modern world? What is this particular? Okay, what is this particular factor that is the integral part of our modern world? Now, without this particular thing or object, our modern world will collapse, all right, and we will go back again to Stone Age. All right, so the answer to that question is electricity. All right, so do you think without electricity, do you think we can achieve this modern world that we have right now? All right, so I think we cannot achieve this because electricity makes our life easier. All right, we have these machines that are run by electricities, computers, cell phones, okay, the buildings that you have right there, the lights that you have right there, okay, and anything around us is run by electricity. Okay? So I cannot imagine a world without electricity. Okay? So, the question here is, how do we produce electricity? Okay, we know that electricity is very important in our lives. So we use it every day, okay, in every day any way that we know. But do we know how it is produced? All right. Do we know how it is produced? Okay, so in this video lesson that we have here, we will I will try to discuss to you how it is produced. Okay? So, our topic today is the module 1B, which is electric generators and transformers. And under electric generators and transformers are the basic things. Okay? Basic things how, or basic mechanism under electric generator. So how does an electric generator works? By using the electromagnetic induction. And we will discuss these two devices that we have over here. Alright, we will discuss these two devices over here to better understand how electricity is being produced and being used in so many ways. Alright, so before that, we will going to discuss the electromagnetic induction. Alright, Alright, so in this discussion that we have, okay, so the key question that we will going to answer here is, what is electromagnetic induction? So what do you mean by electromagnetic induction? So the key word here, or the root word here, is induction. So what do you mean by induction? Alright, so the objectives that we have right here is explain how electromagnetic induction works. Alright, so describe how changing magnetic fields creates these moving charges. So in the last video lesson that we had, we discovered that moving charges creates magnetic field. Now this time it's the opposite. All right, it's the opposite. We change the magnetic field and eventually we create moving charges or current, to be specific. All right, next one is identify the variables that affect the current produced in an electromagnetic induction. So there are some variables that affects this electromagnetic induction that we will going to discuss today. in this session. So let's try to find them all out in this topic that we have right here. All right. So what is electromagnetic induction? So electromagnetic induction is the process of using magnetic field to produce voltage in a complete circuit. All right. So we will going to use magnetic fields in this process. We will going to use magnetic fields in this process to produce voltage. Now, in order to create a current, or in order to create a moving charges, the circuit must be complete for you to have this. All right. So basically speaking, voltage is being produced or being induced, all right, in this process, followed by current. All right. So without voltage, there will be no force. All right. There will be no force that will push the charges, all right, to move from one place to another. Now the question here is, how do we use this magnetic field? All right. So how do we use this magnetic field to produce or to induce voltage? Now, there's one person who can answer that, and that is Michael Faraday. So, Michael Faraday was inspired by the work of Hans Christian Ørsted, and he wants to devise an experiment, or he wants to create an experiment which is the exact opposite of what Ørsted did. Alright? Which is the exact opposite of what Ørsted did. So he wants to find out if he can produce an electric current by just exploiting the magnetic field. Right? By just exploiting the magnetic field. And after the experiment, after several attempts on that experiment, alright, he got a success, alright? He got a success on obtaining such information about this topic that we have in this session. Alright, so he found out that as he moved the conductive substance through the magnetic field, this conductive substance induced an electric current on it as long that this substance moves along with the magnetic field. Alright, so he coined the term electromagnetic induction in this process. Okay, he coined the term. He called it, or he called the process electromagnetic induction. He found out that only by moving the conductive substance or the magnet, either of which, all right, you can induce a current into the wire or the conductive substance. All right, so okay, so this is the basic idea. If you move a magnet near a coil of wire, the current will be produced. So, we called it electromagnetic induction because moving magnets induces electric current to flow. Now, according to Merriam-Webster, the word induce, alright, so the word here, induce, means to cause something. Alright? It means to cause something. So, moving magnet, alright, moving magnet is the one that will cause the electric current to flow. So, hence the word electromagnetic induction. So, alright, so basically, in our video lesson about the electric motor, alright, in our video about the electric motor, we have an idea there that the moving electric charge creates magnetism, or basically magnetic field, alright? But in our discussion today, alright, in our discussion in this session, we have the opposite. Changing magnetic field can cause electric charge to move. Alright, so changing magnetic field will cause electric charge. So as you can see, they are exact opposite to each other. Okay, so you can reverse the other one and make another process. Okay, so that's the third idea here. So the current is only produced if the magnet is moving because the changing magnetic field is what creates current. So what is this? So how do you change the magnetic field? By just moving the magnet into the coil. So technically, if the magnet is not moving, or simply the magnet is stationary, or the current is zero. Alright, so the current is zero. So the question here is, how do we change the magnetic field? So, let's take a look at this next idea that we have right here. So, if the magnetic field is increasing, the induced current is in one direction. So, what do you mean by increasing magnetic field? So, how do we increase the magnetic field? And the second one is the field is decreasing. If the field is decreasing, the induced current goes to the opposite direction. So in this case, how do we decrease the magnetic field? All right, so we have this picture. Now we will not use this picture. Let's go to our simulation. All right, so our simulation today is made possible by PET. All right, so University of Colorado Boulder. All right, so you can visit their website on the description below to access this simulation. All right, so what we have right here is a simulation on how electromagnetic induction works. All right, so as we have seen earlier, the statement that only by moving the magnet in and out of the coil, that's the time that you can induce a current on the wire itself. All right, so you can induce the current, or you can do it vice versa. The conductive substance, if you move it along the magnet, all right, so you can still induce a current. All right, so there you go. All right, so the question here is, how do you change the magnetic field? So how do you change the magnetic field? By just moving the magnet. Okay? So simply, the question is simply answered by number 1, by flipping the polarity. So as you can see, as I flip the polarity, I induce a current in the wire. Alright? So I induce a current in the wire because as I flip the polarity, I change the magnetic field's direction. Alright? As we all know, North Pole and South Pole's magnetic field have different direction. Alright? So these two poles of your magnet over here has two different directions. So by changing the polarity, you change the direction of the magnetic field. Alright, so similar thing that we have right here. So if you flip the polarity, you change the direction. So sometimes it is north and sometimes it is south. So as this one rotates, okay, continuously, you induce a current in this coil of wire. So you change the direction of the current. So if I open the field over here, you can see that the magnetic field is constantly changing direction as the magnetic poles flip on this side. Okay. Now, what's the other answer? All right, what's the other answer? How do you change the magnetic field? By just moving the magnet. So, as you can see here, if you move the magnet close to the coil, you increase the magnetic field. As you move out the magnet away from the coil, you decrease the magnetic field. Now, doing it in a higher rate, all right? So, doing it faster, okay, you change the magnetic field faster. All right? Now, doing it slowly, you change the magnetic field in a much slower pace. All right? So, again, how do you change the magnetic field? By just moving the magnet in and out of the coil. As you move the magnet near the coil, you increase the magnetic field. As you can see here, the magnetic field, or in this simple detail in this simulation, okay, so the magnetic field inside this coil lights up when the magnet is near, and it becomes darkened as the magnet goes away from or moves away from the coil. So it means that as it lights up, it increases, then as it moves away, it decreases. So, alright, so it means that you change the magnetic field by just moving the magnet near and away from the coil respectively. Now, the manner on how you move it is the rate of movement of your magnet. Alright, so that will be the topic later. Alright, so that's the question. How do you change the magnetic field? By just moving the magnet. By moving the magnet near the coil, you increase the magnetic field. By moving the magnet away from the coil, you decrease the magnetic field. So, in the other statement, if the magnetic field is increasing, the induced current is in one direction. So what do we mean by that? So we will use a galvanometer or voltmeter in this case that we have right here. So this is not a galvanometer. This is the voltmeter that is available in this simulation that we have right here. So as you can see, it has a positive and negative or portion. All right. Now, as the magnetic field increases, Alright, so as I put this magnet near the coil of wire, so as you can see, the arrow goes to the positive direction. Then as I decrease the magnetic field, it goes to the opposite direction. So let's repeat it one more time. Okay, so it goes to positive and it goes to negative. Alright, so it goes to positive and it goes to negative. If you have the south pole facing the coil. Now, what if we flip the polarity and the north pole is the one facing the coil? So what will be the effect here? Okay, so will it still be the same? Okay, so let's take a look. Alright, so this time it goes to negative as it increases. Then as the magnetic field decreases, it goes to positive. So let's see. Alright, so increases, decreases, increases, decreases. Alright, so that is the effect of increasing and decreasing magnetic field. Now, what do we mean by the positive and negative signs over there? So, the depth or the meaning, all right, so it tells us the positive and negative sign on this particular voltmeter tells us the direction of the current. If it is going to the negative, all right, if it is negative, meaning to say the current is going from negative to positive, and if it is positive, it goes the other way around. All right, so in opposite direction. So it tells us the direction of the current that is inside this conductive substance or the current carrying wire. All right, so that is what we meant by this particular statements that we have right here. All right, so let's move forward. All right, so that is the electricity by induction. So if you put these magnets, all right, if you put this permanent magnet in a rotor, so you know already what is a rotor. That is a spinning disc, okay, which is a part of a motor. All right, so if you put this permanent magnet in a rotor, it will induce a current in this coil of wire over here. All right, as long that the polarities of this magnet flips time and time again, the electric current will be continuously produced in the process. All right, so now when the rotor stops, the electric current production or the induced current will also, or induction of current will also stops in the process. Okay, so that's the effect of that. Okay, so that is electricity by induction. All right, so a moving magnet induced current in a coil only if the magnetic field of the magnet passes through the coil. So the thing here is passes, not putting it through the coil. Alright, so the word here is passes. Alright, so what do you mean by this one? Okay, so let's go back to our Andy simulation that we have right here. Okay, so now as you can see here, now only by making this magnet passes through the coil. Alright, so as you can see here, as I move this magnet away from this coil or on this distance from the coil, as you can see, there is no current induced. But if I move it near the coil, that's the time that you induce current. Now, if I put it in the middle of the coil without doing anything, right? So if I put it in the middle of the coil, it doesn't induce a current, all right, in the process. It doesn't induce, all right? So it doesn't induce a current. Only by passing it through the coil, so only by passing it, the way that I do it right here, only by passing it through the coil, that's the time that you will induce a current inside. All right, that's the time that the charges inside this coil of wire will start moving at a certain direction. All right, so that is what the statement means. All right, so okay, so with that, we have now an idea that only a magnetic field that passes through the coil induces current. So in short, Michael Faraday found out that the rate of the movement, so the rate of change of this magnetic field through the coil is proportional to the voltage that is being induced. Alright, so as we all know, in a formula of rate, okay, every time that we encounter a formula of rate, so example of a formula of rate is velocity, alright, or even the rate itself, alright, is a formula. Now, in a velocity formula, there is distance over time. In a rate formula, there is also the entity called time. Alright, so there is an entity called time on that particular formula. Alright, so whatever it is on the formula of rate, alright, there is always time included. Okay, that is a rate. So rate is, in this case, is how fast did you change the magnetic field? Alright, from 1 to 0. Alright, so how fast did you change the magnetic field? That's the, okay, will it have an effect on the induced voltage according to Michael Faraday? Yes. All right. So, according to him, it is proportional. So, as you increase the rate of change, you increase also the induced voltage. Okay. Now, what about the time? All right. So, what about the time that is on this formula of rate that we have right here? According to him, the time of change, if the time of change in your magnetic field is less, all right, or low, then the voltage that is being induced is high. Okay, so in short, rate is directly proportional to voltage and time is inversely proportional to voltage respectively. All right, so that is what he found out on his experiment, okay, about electromagnetic induction. All right, so okay, so moving on, if we increase, according to him, that if we increase the rate at which this magnetic field is moving through the coil, we can increase the induced voltage. So as you can see on this diagram that we have over here, now if I make it to 4 meters per second, the voltage or the volts that is registered in this voltmeter is suddenly increased to 0.64. So, the rate is directly proportional to the induced voltage. So, similarly in our simulation, okay, similarly in this simulation that we have right here, so if we decrease the rotation, okay, the speed of rotation, so if we decrease the speed of rotation of this magnet over here, we also decrease the amount of voltage that are being induced, right? So more so increasing it. So that's the rate of change in your magnetic field. So, all right, so we are now done. All right, so we are now done with the first factor. Okay, we have already encountered the first factor, and that is the rate of movement by the magnet. Okay, movement of the magnet. Okay, so as we all know, the magnet has magnetic field, so the rate of movement of your magnet certainly also affects the change in the magnetic field. Alright, so that is the first factor that we have over here. So what is the key idea? The key idea here is as the rate increases, as the rate of the movement of your magnet increases, it will affect the change in magnetic field. Also, it will increase. So what will happen is the voltage will also increase in the long run. Right. So let's go back to our simulation and find out the second factor. Alright, so the second factor that we have right here is the strength of the magnet. Alright, so the strength of the magnet. Okay, so let's take a look. If the strength of the magnet certainly affects the electromagnetic induction. Alright, so let's start first with 20% strength of your magnet over here. And let's take a look at the light bulb. What will be its effect of the strength of this magnet, 20% of the strength of your magnet on this light bulb. Okay, so at constant rate. Okay, so as you can see here, the light bulb is somehow dim. All right, Now, if we increase the strength of the magnetic field, what could be its effect? All right, so, or the strength of the magnet. So as you can see, it has a great effect. All right. So as you increase the strength of the magnet, the induced voltage also increases. All right. So the induced voltage also increases. So they are directly proportional. So let's go back to our board. Write down the second factor, which is the strength or... All right. So this is the strength of the magnet. Of the magnet. All right. So what is the idea here? So magnetic field is symbolized as B. All right. So the strength of the magnetic field, as it increases, the voltage induced also increases. All right. So let's go back to our simulation and find out the third factor. All right. So we will reset this one again. All right. So what is the third factor? Okay. So let's see the number of loops over here. All right. So let's see the number of loops over here. Now, if I decrease this one into 1 and run at a constant rate, okay, so what do we see? Okay, it is somehow it is somehow bright. All right, it is somehow bright if we have one loop. Okay, so what will be the effect if we increase this number of loops that we have right here? Okay, let's see. All right, so the effect is directly proportional. So if we increase the number of loops, the induced voltage will also increase. All right, so there is a difference in terms of brightness. There is a difference in terms of brightness between one loop and 3 loops. Right, so let's go back to our board and write down the third factor, which is the number of loops. So the idea here is, as we increase the number of loops, the induced voltage also increases. All right, next one, the fourth factor. Let's go back to the simulation. All right, so the fourth factor that we have right here. All right, now the fourth factor is okay. We will have a constant number of loop and a constant rate. Now this time, to better visualize it, all right, so to better visualize this one, we will use a voltmeter. All right, so let's see. How about the loop area? All right, what is the difference of a lesser loop area to a higher loop area? All right, let's see. At a constant rate, let's see. Okay, so as you can see, it touches on this mark over here. So it touches on this mark over here. All right, so let's see if there is an effect. All right, if the loop area has an effect on the induced voltage in this process that we are doing right now. Okay, so we will increase from 20 to 100%. All right, so as you can see, it increased all right, by about 2 ticks on our voltmeter that we have right here. So from this part, all right, so from this part, it increased to 2 ticks. It is now on this part that we have right here, on this okay, measurement. Okay, so truly it increases. So meaning to say that the loop area has an effect on your induced voltage. So by how? How does the loop area, okay, so how does the loop area affect the induced or the electromagnetic induction? So if you're going to take a look, all right, so if you put some field on your simulation, all right, in a lesser loop area, all right, there's what they call flux. What do you mean by flux? That is the amount of field passing on a certain area, all right? That is the amount of field that is passing on a certain surface area, all right? So that is flux. All right, so as you can see here, there are few magnetic field that are passing on that certain area, okay, over time. All right, so there is a small amount of magnetic field that is passing on that area, all right, over time. But if you increase the loop area, we have now a lot of magnetic field passing on that certain area at a given amount of time. Alright, so the flux is greater if you have the loop area, if your loop area is greater. But the flux is less if your loop area is also less. Okay, so that is the effect of the loop area. So as you can see here, the magnetic field, alright, is increased, okay, when the loop area is greater. So let's go back to our board and write down the factor. Okay, so the fourth factor that we have right here, loop area. Okay, so the loop area. So the loop area, as the area increases, as the area of the loop increases, the voltage induced also increases. All right. So let's go now to the fifth. All right, to the fifth part, which is, let's go back to the simulation once again. Okay, so in this case, we'll just slow down the rate of movement of your magnet. Okay, so as you can see, there is a position. All right, so as you can see here, there's a position in your magnet in which the light becomes dim and it grows brighter again. All right, so there's a position. Okay, so let's see what is that. Okay, so this one, as you can see, the light bulb glows brighter. Okay, let's play it once again. All right, so as you can see here, the light bulb shuts off. All right, so the light bulb shuts off. So in this position, okay, of your magnet. So if we continue to play this one, okay, so on that position, the light bulb glows somehow brighter than the previous one. Okay, and on this position, it is somehow bright. So let's see if we go back again to horizontal position. All right, so as you can see here, the light bulb is shut off. All right, so the fifth and last factor that we have right here is the position of your magnet. Position of the magnet. Okay, so what about the position of the magnet? All right, so if it is perpendicular to your coil, all right, so if it is perpendicular to your coil, the magnet is or the voltage induced is greater. So if it is perpendicular, so the voltage is greater. Okay, so if it is parallel, all right, if it is parallel, the voltage that is induced is 0. All right, so basically, okay, if we find out the theta here, so we will use, in this case, we will use the trigonometric function cosine. All right, if the theta is 90 degrees, or rather, all right, if the theta is 0 degrees, right, so if the theta is 0 degrees, that is perpendicular. And if the theta is 90 degrees, that is parallel. All right, so in this process. So, meaning to say, the position of the magnet affects the amount of voltage that is being induced all throughout. Okay? All throughout the electromagnetic induction process. So, these are the five factors. And let's put this one into a working formula. Let's put this one into a working formula so for us to better understand how these factors work. All right, so with that, Faraday developed a formula that consolidates those factors, and we have it right here. So the voltage is equal to the negative number of loops times the magnetic flux over here. This is the magnetic flux. The change in flux divided by the change in time. So we are dealing with rate here. So the time is over here. All right, so the time, we have still the time over here. Yeah. All right, so okay, so Faraday learned that the rate in change of flux, the rate in the change of flux affects the current that is, or the voltage that is being induced in your process. Okay, in the process. So this is the Faraday's law of electromagnetic induction formula. So let me repeat again. This is the voltage. All right. So this is the voltage. This is the number of turns. All right. This is the change in flux. All right. So we have the change in flux. So over here. All right. So that is the change in flux. Now, if you break down the formula, or if you break down the change in flux, it has a formula of the magnetic field, the strength of the magnetic field, and we have the area. All right. So this is the area. All right. So this is the strength, magnetic field, or the strength of the magnet. Okay, strength of magnet and the position of the magnet. Alright, so that is in cosine theta. So remember, cosine 0 is 1 and cosine 90 is 0. Alright, so cosine 0 is 1 and cosine 90 is 0. So meaning to say, at cosine 0, you will achieve maximum amount of voltage which is being produced, divided by the change in time. Alright, so you can use that one. Alright, you can use this formula if you want to prove that the factors that we listed a while ago. Alright, you can use this formula to prove that those factors have really a significant effect to the amount of voltage that is being produced. You can create, or you can put a hypothetical value, all right, for you to find out if these factors really affect the electromagnetic induction. All right, so that is the formula of Faraday's law of electromagnetic induction. Now, to visualize it, we have it right here. Okay, suppose the coil is spinning, all right, in this process. So the coil is spinning at different directions. So let's find out what is the effect of that spinning motion in the flux and the current that is being encountered by the coil that you have right here. Okay, let's start with the flux. Now, at this position, the flux is maximum. Why? Because over the large area, all right, so over this large area that you have right here, it captures, all right, it allows more magnetic field to pass on that certain area at a certain amount of time. All right, at a certain amount of time. So there are a lot of magnetic field passes on this area at a certain amount of time. So that is the reason why the flux on this point A is maximum. Okay, meanwhile, the current is 0. Alright, because what is the reason behind that one? Why the current is 0? It's because the coil is not moving. Alright, so the coil is not moving, so the current is 0. It starts to move. Okay, when it starts to move, the flux now starting to decrease. Alright, so the flux now starting to decrease, and you have now from maximum flux to decreasing number of flux. Alright, you have now a change in magnetic field. Alright, so the coil is experiencing now the change in magnetic field. So that's the time now that you will induce a voltage and a current. Alright, so you will now induce a voltage, so the current will increase respectively. Right, so the current will increase respectively, and as the coil of wire approaches at this horizontal position, so probably this is the 90 degree. All right, so this is the 90 degree position. The flux becomes 0. All right, so the flux becomes 0. Then the current is now at maximum. Now, why the current is now at maximum? Because the change of magnetic field from maximum to 0, all right, is great. All right, so the change in magnetic field from maximum to 0 is great. So there is a great in the current that will be induced will also be affected. All right, it will become All right, so the current that will be produced is or will be at its maximum. Okay, because the change of the magnetic field that you have right here approaches to zero, from maximum to zero. So that's the time that your current that will be produced is also maximum. Now, as it completely rotates again to another position at point D, the flux now is starting to increase. Right? So the flux now is starting to increase. So because there are a lot of magnetic field that is now captured in a certain area. All right? There are a lot of magnetic field that is now moving in a certain area. So it will now starts to increase. And the current now is starting to decrease. All right? It is starting now to decrease. And as it approach to point E, all right, so as it approaches to point E, the flux now will achieve its maximum amount. All right, so the coil now will have its maximum amount of flux entering that certain area of your coil, and the current now is zero because from zero to maximum. All right, so as the coil move from zero flux to maximum flux, the current also that will be produced at that process will be also zero. All right, there will be an effect on the induced current. Now, more so at point F, all right, so at point F, the flux starts now to decrease. All right, it starts now to decrease. Then the current now is starting to increase, but it will increase into the opposite side. It goes now to the positive side. Now, a while ago, the current increases on the negative side. All right, so the one that you have right here, the diagram that you have seen right here, has a pattern of flux that is going at maximum amount, then it will decrease, and then it will come zero at certain position. Now, also, the amount of flux dictates the amount of current being induced in the process. Alright, so the current goes to negative, alright, and so, at some point, it will go to the positive side when it increases. All right. So the diagram that you see here is a no, the diagram that you see here is a good example of this. This diagram shows how the alternating current, all right, process work. Okay. So how the alternating current is being produced. All right. So that is the Faraday's law of induction in this particular diagram. Okay. So, we go now to the applications of this Faraday law of induction. So, for us to better realize its importance. All right. So, we have here a forever flashlight. So, this flashlight that we have right here doesn't have okay, so doesn't you don't need to constantly replace the battery. All right, time and time again when it drains out. So all you need to do is to shake the flashlight and it will recharge the battery that is inside. As you shake it, then when you shake it, it will produce an electricity that will charge up this battery. So it doesn't run out of batteries. All right, next one. Transformers also use electromagnetic induction. That is a topic for another day. All right, so we will discuss that the idea on how the transformer works. Also, mobile chargers, all right, mobile phone chargers, laptop chargers also uses electromagnetic induction. All right, so there are myriad of device that uses electromagnetic induction. You just don't take notice it. All right. So another example of devices that uses electromagnetic induction is the electric generator. Okay. There are two generators that we have right here. We have DC generator and AC generator. So if you have an industrial generator, it is as big as this. All right. If you have a residential or household generator, all right. So it looks like this. It is a portable generator that we have right there. Right. So you just fill it up with petrol. You just fill it up with petrol and it will work. Right. So same thing that we have over here. So in generator, it produces electricity. It uses mechanical energy to produce electricity. All right. So the other one is microphone. All right, and metal detectors that are found in some establishments. All right, so let's start first with the microphone. So how does a microphone become a device that uses an electromagnetic induction? So, as you speak in a microphone, your sound waves, all right, your sound waves will pass through this diaphragm. So the diaphragm over here, this diaphragm will convert that sound wave into a mechanical energy in a form of vibration. So the diaphragm, underneath the diaphragm, there is a coil. So as you can see here, these are the coil. All right. So the coil now will, okay, the diaphragm will vibrate, and along its vibration, the coil also that is attached to your diaphragm will also vibrate in the process. Alright? So it will vibrate in the process. So as it vibrates, it creates or it induces a current. Alright? So it induces a current as it vibrates and it goes to the speaker. Then you can now hear your voice. Alright? You can now hear your voice on the speaker as you speak on the microphone. So basically speaking, microphone is the opposite of speaker. Alright? So the microphone doesn't need to be connected in an electrical outlet. All right, it doesn't need to be connected in an electrical outlet, but it needs to be connected to a speaker for you to hear your voice. The speaker is somehow the opposite of your microphone because speaker is similar to your electric motor. The speaker will not work without electricity. All right? The speaker will not work without electricity. The vibration that the coil will create on a speaker will only vibrate if there is an electricity passing through the coil inside that speaker. All right? So metal detectors. Okay, so the metal detector, so there's one that will on this side of the metal detector, it will create a magnetic field. So when something that is metallic passes through the middle part or this point in your metal detector, all right? So what happens here is, all right, what happens here is it induces the current, all right? It induces the current in your metallic object, in your belongings, and it creates this magnetic field around it. Then this magnetic field is being picked up by another coil on the other side of the metal detector. Thus, the metal detector will trigger a sound if it detects a metal in your belonging. So remember what Hans Christian Ørsted said, that moving charges creates magnetic field. So in this process that we have right here, the magnetic field, all right, so the magnetic field over here will trigger or will create a moving charge on your metal belongings, and it will create its own magnetic field. Then this magnetic field will be picked up by another detector. Then it will trigger a sound on your metal detector. All right, so same way that we have right here, this metal detector button. All right, so we have right there. So some security guards uses this one to detect or to find out if you have metallic belongings on your bag or something like that. All right. So, okay. So before we go to this, I want to show you some some demonstration. All right, before we focus about Michael Faraday. So let's take a look some demonstration using electromagnetic induction. All right, so I have right here. Okay, so remember the formula of electromagnetic induction. So the negative sign there, okay, the negative sign there is called the Lenz's law. All right, so in this video, we will not discuss the Lenz's law, but in this demonstration, I think you might get the concept behind Lenz's law. All right, so as you can see here, I will use a neodymium magnet. All right, and let's play this one. Okay, so I have a cylindrical and I have a ball neodymium magnet. So these are very strong magnets. All right. This will give us certain results. All right, satisfying results in this process. Okay, so we have it, the cylindrical magnet. Right, so it is magnetic. Okay, it's very strong. All right, so now as you can see, the PVC pipe. All right, so the PVC pipe on this video. All right, it is not. It is non-magnetic. So it doesn't. The magnet is not attracted to that one. So okay, you can pause the video if you want. So if I drop the magnet on this PVC pipe, all right, what do you expect the time of fall? All right, what do you expect the time of fall of of our magnet as I drop this magnet inside this PVC pipe? All right, so you can write down your answer in the comment section of this video. All right, so as I drop the magnet, all right, so as I drop it once again, all right. So that's the PVC pipe. Okay, so if I drop the ball magnet inside the PVC pipe, if I drop that ball magnet inside that PVC pipe, will it have the same effect? All right, so it's the same thing, right? So it is somehow fast. It's It is somehow faster. All right. So, okay, let's have another video. This time I will drop the magnet inside a aluminum tube. Inside an aluminum tube. So, I have it right here. All right. So, this is the same magnet that we have right here. Okay, so the aluminum is non-magnetic. Alright? It is non-magnetic. It is paramagnetic. So, in this case, what could be the time of fall of our cylindrical magnet that we have? Okay, so will it be the same as the PVC pipe or it is different? So, write it down in the comment section. Write down your answer in the comment section before you play this video. All right. So as you can see, the fall of the magnet falls. All right. So the magnet falls much slower than the one in PVC pipe. All right. So the one that I'm doing right here. All right. So the one that I'm demonstrating right here is the negative sign on your electromagnetic induction formula. Okay, so more so, let's take a look at the ball magnet when we drop it on the inside the aluminum tube. If we drop the magnet inside the aluminum tube. Alright. So, okay, so what is the time of fall? Okay, so the ball magnet falls slower than the one in the PVC pipe. Okay, so I have another last video, last demonstration over here. Okay, so you might get the concept of Lenz's law. As we all know, aluminum is a conductor of electricity. Alright, it is a good conductor of electricity. So I have here another set of magnets. So this is another shape of magnet. So this is a cube. Alright, so rectangular cube magnet. So, alright, so as I pass this magnet over that aluminum tube, alright, what will happen to the aluminum tube as I pass this magnet over it? Alright, without contact. Alright, so without contact, so what will happen to that aluminum tube? Will it move or not? Okay, so you can pause this video. Alright, you can pause this video if you want to and then write the answer on the comment section. So let's take a look. All right. All right. So the explanation behind this one is, as I pass this magnet through this aluminum tube, all right, so as I pass this magnet through this aluminum tube, it creates or it induces a current on it. So basically, the tube creates an electric current. Now, going back to the idea of Hans Christian Ørsted that moving charges creates magnetic field. So as this current moves on this aluminum tube, it creates its own magnetic field. So meaning to say that this tube that we have right here creates its own magnetic field that comes interacting with the magnetic field coming from this permanent magnet. So that is why the magnetic field that you have on this aluminum tube and the magnetic field from the permanent magnet creates these magnetic forces that enables this tube to move from one position to another. So, all right. Only if I pass that magnet on that particular tube, that's the time that it will induce a current. Now, if I didn't pass that magnet on that aluminum tube, it will not create this current and it will not move. All right? So that is Lenz's law, right? In the process. So Lenz's law. Alright, so that is the negative sign. Alright, the Lenz's law is the negative sign on your electromagnetic induction. Alright, so let's go back now and finish up our video lesson for this session. Alright, so we have a person in highlight here. We have Michael Faraday. Okay, so we have Michael Faraday. So who is Michael Faraday? Okay, Michael Faraday is the one who he is the proponent of electromagnetic induction. These are the things that he used during his experiment, all right, finding out the electromagnetic induction. And what is good about Michael Faraday that we should follow is that despite being little formal schooling, so he has a little formal schooling. He didn't went to high school or even college. He just went working in Royal Institution in London. All right. Upon working in the Royal Institution in London, he taught himself how to learn things by reading some research in that institution. Okay, every time that he cleans this book, every time that he arranged this book, he is a bookkeeper, by the way, in Royal Institution. So every time he arranged the books in Royal Institution, he constantly or he always reads what is the content of these books, the research that he always arranged, and eventually with a bit of self-learning, all right, with a bit of self-learning, he discovered electromagnetic induction. All right, he discovered electromagnetic induction. He has now an idea, okay, on how this electromagnetic induction works. And because of his discovery of electromagnetic induction, the modern world that we know right now, all right, the modern world that we know right now is possible, okay, because of him. Okay, so that is Michael Faraday. The moral lesson of this topic that we have right now is, okay, do not make something, all right, do not make something as a hindrance to you to be successful. All right, instead use that obstacle for you to improve yourself. All right, just like what Michael Faraday did. He is a self-learned individual, and upon learning by himself, he discovered so many things. All right? So with that, that ends up our video lesson for this session. So I hope you did learn something from this topic that we have right here. So if you did learn something from this topic, just hit the like button on this video, subscribe, and hit the notification bell for you to be updated with future science video lesson like this in the future. Alright, so don't forget to write down in the comment section. It will help me a lot in improving my video lesson in the future. Alright, so that's it, guys, for now. Let's see each other next time. Peace out. Alright, peace out.
みたい子供なのね夢を追って傷ついて嘘が